Hello everyone, Lieutenant Colonel Jewett here to discuss with you the basics of thrust to weight and wing loading ratios. But before we begin, I want to look at this photograph. Two F-16s out of the 457th Fighter Squadron, Fort Worth, Texas, reserve unit there. In a vertical climb, this F-16 does have a pretty spectacular thrust to weight ratio in this pretty amazing photograph. Let's begin. For those of you in Aero 210, you're definitely going to see this question. For a small lightweight aircraft design, let's think of it as a small lightweight fighter like, say, the F-16, which would you prefer, more thrust to weight and less wing loading, or more wing loading and less thrust to weight? For those of you in Aero 315, this is a lot of background information, but good for you to know as well. I'm going to come to the board here, or the paper, and really quick, when we're talking about thrust to weight and wing loading, if you recall what wing loading was, and this is one section of one wing. If I was to look at 1 square foot, for example, of the wing, just how much weight is it actually lifting? So the ratio is weight over area, and more specifically, the weight at takeoff over the area of the wing. And that's what S is. S is defined as the plan form area, or the entire area of the wing, even the part going through the fuselage. Okay? So that's just a little background. Weight at takeoff is measured in pounds of force, and S, planform area, is measured in area squared, or for our purposes in this demo, we're talking about feet squared. Okay, let me get to the question at hand. So when we're looking at thrust to weight ratio, that's pretty self-explanatory, probably a little bit more so than wing loading. Let me just plot them against each other. If I look at the thrust to weight ratio, effectively how much thrust is produced versus the weight of the aircraft. And we're going to be more specific here and say the weight at takeoff versus the thrust measured at sea level, compared against the weight at takeoff over the planform area. And now these are getting bigger in their respective axes. So the question says, it makes it clear by looking at the equation. We're going to get to the equation first. I'd like to discuss this from a notional point of view. Thrust to weight is nothing more than a fraction, right? Thrust to weight. It's also a division equation. It's also a ratio. So thrust to weight is measured in pounds force over pounds force. That makes it a unitless parameter. So it comes out with just a number, let's just say 0.7 for now, thrust to weight ratio. If it's bigger than 1, it has more thrust than it has weight, and it could probably accelerate in a vertical climb to a certain altitude. Well, if we hold the weight fixed, let's assume that weight is fixed, and we want to grow this ratio. That means thrust has to get bigger, right? And that means the overall resultant fraction, or the ratio, also gets bigger. Well, how do you make more thrust? What's the thrust produced by in a jet aircraft? It's produced by the jet engine. So if the thrust is getting bigger, what can probably be said about the engines? Again, notionally, we could probably say that the engine is getting bigger. Now we're working on optimizing really efficient engines, but again, notionally speaking, if I have a bigger engine, what powers the engine? Well, lots of air and lots of fuel, okay? Well, if you have more fuel on board, where are you going to put that? So what else is probably going to grow? The amount of volume you need to put that fuel somewhere. Well, if the engine's getting bigger, you need more fuel, more volume, what can probably be said about the aircraft? It's probably also going to get bigger. Now, let's think about what the taxpayer is thinking, and your congressman, and the program manager acquiring this fighter. What do you suppose dollars are going to do now? They might also go up. So that is, again, notionally, if you want more thrust, if you want infinite thrust, everybody wants more thrust, you got to have more of this, right? Well, now let's look at the horizontal axis. Again, we're holding weight fixed. So let's look at the fraction. Weight to planform area ratio is known as wing loading. So how do I get this fraction bigger? Well, if weight is fixed, what happens if I make the S, or the wing size, smaller? The wing loading gets bigger, right? So again, notionally speaking, we like to go down and to the right when we compare these two. And for those of you in Aero 210, you're going to see this later as a constraint diagram, and it's going to help in your design. Let's go over to the equation, just like the question's asking. We want S to get smaller. Well, how does S get smaller? Let's assume that the customer has fixed the payload weight, so that can't change. Well, what happens then to make S smaller is that the denominator should get bigger. So you want a larger wing loading. Let's look at the term with thrust to weight in it. The weight of the engine relative to the wing size. If I drive thrust to weight down, that's going to drive this value down. And since this is subtracted here, I don't want to subtract too much from the denominator. I want to drive this down. That'll keep the denominator bigger and in turn make the planform area smaller. I hope you're able to learn a little bit from this tutorial. I'll see you in class.